Thank you for the opportunity to present our research. The title of our presentation is The Impact of PWV Data Assimilation in Convective Permitting WRF ARW on North American Monsoon Precipitation Forecast over northern Mexico. And I would like to acknowledge my collaborators, Dr. Castro, Dr. Ariano, Dr. Mocker, and Dr. Adams. So we start with the problem of forecasting North American monsoon precipitation. As shown in these figures, the current operational model do not adequately resolve the diurnal cycle of convection and do not properly represent the organized convection in the Northern American monsoon region. And also we found that there are fewer sources of observational data to be assimilated to the model compared to their availability in the US. The second problem is with the convective permitting resolution itself. Here we have the WRF GFS model on the top panel and the GPM observation precipitation in the lower panel. Although it resolved the convection as shown in the top figures, the WRF GFS terminates precipitation too early and underestimate the mesoscale convective system westward propagation. So here we see the difference between the model and also the observations. So the objectives of our research is to improve the NAM precipitation forecast by assimilating the GPS-derived PWV or GPS PWV to make correction on the model initial PWV. And in summer 2017, we conducted a field campaign called the NAM GPS Hydrometeorological Network. And in this field campaign, we collected GPS PWV from 18 sites. So this doubled the size of the Transect field campaign in 2013. We also collected precipitation data from 16 sites and 7 from Conagua sites. And all the sites are here in the figure on the left. And also we collected satellite precipitation datasets for verification. It is from GPM Emerge Final version 6. And here we have the picture of one of the GPS antennas in Kino, Sonora. In analyzing the data, we classify the precipitation events based on the presence and absence of the inverted trough. Here in the figures, we have the inverted trough marked by the upper level low and also upper level divergence over northwest Mexico and southern Arizona. So we call strongly forced days for the day with the inverted trough, and we call weakly forced days for the days without inverted trough. The former has 9 days and the latter has 38 days. Both, either strongly forced or weakly forced, could create heavy rainfall and wide extent of thunderstorm cloud, as shown in the figure here from the satellite. But in this research, we focus only on weakly forced days because we are assuming that PWV has greater forecast impact. For the WRF configuration, we use 3 nested domains. It is 30 kilometers, 10 kilometers, and 2.5 kilometers, as shown in the figures. We also use the Global Forecast System, or the GFS, for the lateral boundary condition and the initial conditions for the simulation. And for the data assimilation configuration, we use an ensemble Kalman filter from the data assimilation research testbed available in this website. And we use 30-member ensemble, 1 hourly data assimilation or super obbing. Observation error is set to 0.075 centimeters. And the Gaspari cone covariance localization length is set to 0.07. Figures on the right shows the convolution of the GC or the Gaspari cone influence in the domain. The area circled in black has the highest influence of the DA, and we call this GC11. And we will focus on this dense observation site called the GC11 for the evaluation of the variables. So first of all, to find optimal DA configuration, we conduct five experiments varied in the length of the DA cycles as shown in the blue arrows in this figure. It ranges from 6 to 18-hour DA cycles, but they have the same 6-hour spin up prior to the DA cycle, and all of them ends at 12 UTC. And we use one of the events from the weekly force days, which is the August 9, 2017. And here is the result of the testing for the DA cycle length for all experiments. What is interesting here is that experiment 2 exhibits the lowest RMSC at the forecast initial time. So it is at 18 UTC. And it also has the slowest RMSC increase in the forecast mode. So it's between 18 UTC to about 22 UTC. So we use configuration of experiment 2, which has 12-hour DA cycle. And we also simulate control run, which has the similar setup, but without DA assimilation, and we call it no DA. So we simulated all 38 cases, and here is the PWV statistical analysis and computed from the observation side. So here we compare the DA-PWV and no DA-PWV against the observed PWV or GPS PWV. So DA-PWV is closer to the GPS PWV as shown in figure A, and it has lower RMSE as shown in figure B, lower bias as shown in figure C, and high correlation as shown in figure D. But the models, either the DA and no DA, still have this phasing problem, that the diurnal cycle is out of phase compared to the GPS PWV, shown in figure A. Here is the horizontal distribution of the PWV difference computed from all cases. It is the difference of the DA PWV and no DA PWV from 18 UTC to 6 UTC. And over GC11, we see that the DA PWV is lower than the no DA PWV. So this is consistent with the PWV in the sites in the previous slide. And this one is the hourly precipitation from all cases, average over all observation sites. So we compare here the GPM measurement and the rain gauge measurement against the DA and the no DA precipitation. And what is interesting here is that the DA precipitation is closer to the GPM measurement in the last 8 hours. So this is from approximately from 4 UTC to 12 UTC, or from 21 local time to 5 local time. And this is the spatial distribution of the difference in precipitation rate between the no DA and the DA. So this is DA rain minus no DA rain, shown in the figures on the top. And the DA precipitation rate is higher than that of the no DA at 3 to 9 UTC, or even to 12 UTC. And as shown here, that over GC11, the precipitation is higher, even up to 0.1 millimeters precipitation rate from 3 UTC to 6 UTC compared to the no DA precipitation. We also calculated the verification matrix for the DA precipitation and no DA precipitation using the probability of detection as shown in the figure, in the lower figure. And we take the difference here. So blue indicates high forecast scale for the DA precipitation forecast, and red indicates low forecast scale for DA precipitation forecast. So again, GC11 generally exhibits high forecast scale for the DA forecast, and also they are field significance as shown in the percentage in the panels. We look at the difference between the DA cloud top temperature and the no DA cloud top temperature. So here is the DACTT from 21 to 0 local time, or from 4 to 7 UTC. And DACTT is colder than no DA. So the colder CTT matches with the precipitation in the DF forecast that we see in the previous slide. So it's consistent. We also look at the difference between the DMU cape, or the most unstable convective available potential energy, and also the no DMU cape. The DMU cape is higher than that of no DA at 17 to 23 local time, or from 0 to 6 UTC, and it is approximately 3 hours before the precipitation begins. So this again agrees with the GPS PWV DA impact that it's shown in the previous slides. And we know higher mu cape means higher instability in the DA forecast. And finally, we also look at the 2-meter dew point forecast. Here is the difference between the DA and non-DA for all 38 cases over the GC11. And we see that the dew point is higher than that of the no-DA at 11 to 23 local time. And it is approximately 9 hours before the precipitation begins. So this again agrees with the GPS PWV DA impact. And as we know, higher dew point means more near surface moisture and higher instability in the DA forecast. So in summary, the GPS PWV assimilation exhibits an impact on the atmospheric preconditioning and precipitation. And here we see the DA forecast increases moisture near surface and decreases moisture aloft, and so it increases the instability in the atmosphere. And as a result, the DA forecast generates deeper cloud and more intense precipitation in the later hour of the forecast. In contrast, the no-DA forecast decreases moisture near the surface, but increases moisture aloft. So the stability decreases. The instability decreases. And as a result, the no-DA forecast generates deep cloud, but less intense precipitation. So in conclusions, the 12-hour DA spin-up improves the model's memory of PWV. And the DA forecast adjusts the model PWV closer to the observed data than those of the no-DA. But still, the problem is of phasing is still there. The DA forecast also preserved the model precipitation after 3 UTC up to 0.1 millimeters, especially in the GC11 and also to the south. And in this presentation, we do not show the south impact of the in the precipitation. And the DA does not necessarily improve the magnitude of the model precipitation and the westward propagation. And it seems that there are other mechanisms and physical processes that also derive the precipitation in the model. And finally, the area with high density observation has the most improved forecast. Thank you for your attention, and now I take questions.